Welcome back for the final lecture on trigonometric functions. So this is really trigonometric functions part 2. Last time we talked about degrees versus radians. We talked a little bit about what trigonometric functions are, at least their formulas, and we took a look at their graphs, and we talked about how we figure out things like the sine of pi over 4 is equal to root 2 over 2. We made that table. Today we're going to talk about solving equations. So the idea behind this is, what if we have a sine of x and it's equal to root 2 over 2. Now the answer to this question is not as obvious as you would think, because obviously x equal to pi over 4 is one solution, but there's actually an infinite number of solutions. You can add any multiple of 2 pi. So we'll have 2 pi in here. We'll also see that 3 pi over 4 is also a solution, plus 2 pi n, where n is an integer. So we'll write that as n is an element of z. Right, z is the set of all numbers, 0, 1, 2, dot, dot, dot. So all nice counting numbers, including the negative numbers, -1, -2, dot, 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 going to the left. So that's what we call the integers. So there turns out to be an infinite number of solutions. You can see this simply by looking at the graph of sine of x. So down here, I put the graph of sine of x. So this would be the graph of f of x equal to sine of x. And if you look at the height, root 2 over 2, it's about right here. And you see when you pass through that height, that yellow graph is going to hit it on this page 1, 2, 3, 4 times. And it's actually going to hit it an infinite number of times. And so what happens is you capture one solution here with this expression, is pi over 4, and then the plus 2 pi in gives you all 2 pi pluses from this point. So that's minus 2 pi. Then over here, there's going to be another plus 2 pi. And then the one below it captures the remaining solutions, one here. And then if you go minus 2 pi, you go there. And if you go plus 2 pi, it's going to go over here, and so on. So there's an infinite number of solutions. Now, in a little bit, we're going to learn how to do this. But first, let me talk a little bit about inverse trigonometric functions, because these tend to frighten students a bit, but they're not that bad when you start to think about it. And so down here, I have the sine function, and then to the right, this is actually the inverse. Oops. Getting ahead of myself. This is actually the inverse sine function. So we'd write this as, if you want, you could write f inverse of x, and that's equal to the inverse sine function. So we write this a number of ways. Some books write it, like I write it usually, sine inverse of x. Other books will write arc sine of x. So it's the same thing, just different notation. So arc sine of x. I'm used to using this notation, so this is typically what I use. Just be careful that inverse does not mean 1 over. It actually means the inverse function. So the idea is that the sine will take you one way. So the sine of x takes us from the left to the right, let's say, and sine inverse will take us back. And of course, the remaining graphs down here, this is the cosine of x. So we could write f of x equal to cosine of x. And this is then the inverse. So f inverse of x is equal to cosine inverse of x. And then this, of course, is the tan of x. I don't need to write f of x equals if you don't like. And then this would be the tan inverse of x. It's the one that's going to go back. So cosine goes one way, cosine inverse takes us back. Whereas the tan of x here takes you one way, the tan inverse takes you back. Now, how do they choose these graphs? I think that's important for you to see, because when you write these down in textbooks, often you'll write down the domain and range of the inverse, and it looks real complicated. but it's actually very simple. So the idea is if you look at this graph, it does not have the inverse the way it's drawn. So what you have to do is pick a piece of it. Sometimes we say, you know, we take a certain branch. And so the branch they take is they start here and just go up to here. And they just look at that one piece. And that one piece has an inverse, and the inverse is given by this graph over here. Just like we did in class, you could trace this on the back of the paper, you know, flip it over, trace it on the back of the piece of paper, switch out the x's and y's, and you'll see you get exactly this. That's why it goes from minus pi over 2 to pi over 2, because this goes from minus pi over 2 to pi over 2. For the cosine, take a look at it. They're taking from 0 to pi because they chose this piece of the graph from here to here as their, and this little piece right from here to here, this does have an inverse, whereas the whole graph does not. So they pick a little piece. And again, if you flip over the piece of paper, trace the graph, this little piece, and flip out x's and y's, you'll see you get this graph here. And then tan inverse, how do they draw this? They just choose one of these pieces, and they choose this piece right here. And they can't take all of it because this whole thing does not have an inverse, right? It doesn't pass this horizontal line test. Hits it lots of times. But if you pick a piece, and then you can say that's what I'm going to take as tan inverse, and we can draw it over here. So it's a real simple idea. All right, so let's start solving some equations. So on solving, we're going to do a lot of these because this is tough at first for students to do. And so we're going to start with this one that we did just a minute ago, sine x equals root 2 over 2. And again, there are two parts to this, just like there should be an x here. Just like finding the sine of pi over 4 is root 2 over 2, there's really two parts. First, you need to know this table. So let's write this table right here. So we have theta, and then we're going to have cosine of theta, and we'll have sine of theta. And then we write theta over here. So we have 0 degrees, pi over 6 degrees, pi over 4 degrees, pi over 3 degrees, pi over 2 degrees. And so remember, that's 0 degrees. Oh, these are radians. I'm sorry. Right? I shouldn't say degrees. I kept saying degrees. These are all radians. Above it, I'm thinking I should write the degrees. So 30 degrees, 45 degrees, 60 degrees, and 90 degrees. But below this, right? Remember, these are not degrees. These are actually in radians. So all you have to remember is the cosine of 0 is 1. And that's easy for me to remember because c becomes 4s. So c is the first. So it's 1. And so then it goes root 4, root 3, root 2, root 1, root 0, divided by 2, divided by 2, divided by 2, divided by 2, divided by 2. And then sine's exactly the same, but the opposite. So it goes root 0, root 1, root 2, root 3, root 4, divided by 2, divided by 2, divided by 2, divided by 2, divided by 2. So there's my table. And so this is going to help me. And I'm also going to need this all students take calculus. So all students take calculus. This will tell me where my basic angles, what quadrant they're going to lie in. So the idea is I look at this, sine of x equals root 2 over 2, so it's positive. So that tells me that my angle can lie in this quadrant or this quadrant, but not these two, because down here the signs are negative. And all are positive here, and the sine is positive over here. Then I just have to figure out which angle gives me root 2 over 2. And so here, the sine of this angle is root 2 over 2, and so it's pi over 4. So my reference angle here is pi over 4. And my reference angle over here will also be pi over 4. And so to find my two angles in standard position, it's real simple. Here's one of them. So one of them is going to be x equal to pi over 4. And now realize if this is one of my answers, I can always go around, right? 2 pi, 2 pi, 2 pi. Or I could even go back from this around 2 pi, 2 pi, 2 pi. So plus 2 pi n. There's one answer. And then my second answer, it's going to go from here all the way over to there. And to find that one, all you're going to do is you're going to take pi, which is the angle all the way around, and then take off pi over 4 to get back. So you take pi and then take pi over 4, and it's going to get you back right there. And so this is going to be equal to, common denominator is 4, so I have 4 pi over 4 minus pi over 4, which is equal to 3 pi over 4. And let me make sure I actually did the top one right. Did I write that down, 3 pi over 4 right? Yeah, I did. Okay, good. So my next answer is x equals 3 pi over 4 plus 2 pi n. And I have n is an integer. So it's 0, 1, 2, 3, 4, or it could be negative 1, negative 2, negative 3, negative 4, and so on. So that's my answer. Now you can always check your answers. So on your calculator, if you take it out, let's make sure you can check your answers, because that's what I like to do on an exam, because it's real easy to make mistakes on here. So first, always make sure your calculator is in radians. So hit mode, and notice my calculator radians is highlighted. And then I'm going to take, let's say, the sine of pi over 4. So second, pi divided by 4. And that works. That's 0.707, which is square root of 2 divided by 2. Great, so that matches. And then try the other one, because I already know if you add 2 pi to it, you get back to the same answer, because a period of sine of x is 2 pi. So it repeats. Then let's try sine of 3 pi divided by 4. Great, and I get the same answer, and then plus 2 pi n. So I feel good with what's happening here. Remember, what's really going on, if you think about this on the graph, I actually switched the colors, but that first answer is finding this point, and then you add 2 pi's to it, or take away 2 pi's, and you get that point, and so on. And then the second answer is giving you this point, and it's giving you, it's giving you this point, and here, let me redo that. So let me show you, because I highlighted the wrong thing. It's giving you, the first one's giving you this point, this answer, and this answer. Oh, they're the same color. Oh, look at that. How lucky am I? All right, so the first one, the blue answer that I wrote down, is giving you these 3, and then the ones in green are given to you by the points in green here. So it's just finding all those answers, all those possible solutions. All right, let's look at another one, because this takes a little bit of time to sort of sink in. So part B, I want to figure out when is the tan of x equal to root 3. So on this one, when I'm working this, I think, okay, when is the sine of x over the cosine of x equal to root 3? So what I need to do is go up to this table, and sometimes on this table what you can do, and I'll often do this, I'll often just take, let me move this up, I'll often make an extra row here if I have to, and I can do tan of theta, because tan of theta is just this number divided by that number. So if you think about it, this number is 0 and that number is 1, so tan of 0 is 0. And then this number is 1/2, and this number is root 3 over 2. So if you think about it, if you take 1/2 divided by root 3 over 2, you'll see you're going to get 1 over root 3. This one divided by this one is the same number, so you're going to get 1. And then this one, root 3 divided by 2 divided by 1/2. Now if you put this on top, this one on top, and this one on bottom, you're going to get back root 3. And then this one, if you want, I guess we could say this one is undefined in some sense, because you'll be dividing by 0. And so if you look down here, which one gives you root 3? Oh, that's pi over 3. Right, so I know one answer is pi over 3. So when I go over here and I do this, all students take calculus. I figure out which quadrant my solutions lie in. So it's positive, so it can lie in this one. Only the sign is positive, so it can't lie in this one. It's positive, so it could lie in that one. And only the cosine is positive, so it can't lie in that one. And so I know over here, I have one answer, which is pi over 3. And then I have another answer, down here, which is also pi over 3. And so when I go to write up my actual solutions for x, I know x is equal to, well, the first angle right here is pi over 3. And then I could do plus 2 pi plus 2 pi plus 2 pi, so I could do plus 2 pi n. But in this picture, you see if you go pi, if you go to additional pi, let me use a different color, you'll see I wind up right where I want to be on this angle. And then if I go another pi, I wind up back here, then pi, then pi. So my answer for this one is just plus pi n. So there's just one answer instead of two. Now if you write down pi over 3 plus 2 pi n as one answer, and you write down the other answer, which is pi plus pi over 3, you did it like we did last time, so that's equal to 3 pi over 3 plus pi over 3, which is 4 pi over 3, plus 2 pi n, you'll get exactly the same solution set. Right, it should include here n as an element of the integers. You can check your answer by using your calculator, so I can take the tan of second pi divided by 3. And I get 1.732 blah blah blah, which is the same thing as square root of 3. You can even add various multiples of pi to it if you want. So if you have second pi divided by 3, and you add, let's say, 5 pi, I should get the same answer back, and I do. Right, so those are all possible solutions for my x. Okay, one last one here to just kind of hit it home. I want to do part C, which is the cosine of 2x is equal to negative root 3 over 2. So I'm going to start with my picture. All students take calculus. I'll try to figure out where this angle here, where this 2x, this is my angle 2x, where does it lie? Well, it can't lie here because all the trigonometric functions are positive here. Now it could lie over here because only the sine is positive, and it could lie down here because the tan is negative, but it can't lie over there because only the cosine is positive. And obviously the answer is negative. So I know my angle is going to be over here. It's going to be over here, and it's going to be down here. And I just had to figure out these two reference angles, so the angle here and the angle there. So the way this works, you go up and see when is the cosine root 3 over 2, and that's going to give you your reference angle. So root 3 over 2, it's pi over 6. So these are both from the x-axis here. This is pi over 6. And this is also pi over 6. And to find my answer, I need to find this angle. Find this, what we call standard form. And so it's going to be pi minus pi over 6. So I'm going to go all the way around and back pi over 6. And that's going to equal 6 pi over 6. Take away pi over 6, which is simply 5 pi over 6. And so 2x, this angle, which is 2x, will equal 5 pi over 6. And then, of course, I can go plus any 2 pi n. So plus 2 pi n. And then my second answer, it's going to go all the way around from here to here. So I'm going to take pi, instead of subtracting pi over 6, I'm going to add an extra pi over 6. And so that's 6 pi over 6 plus pi over 6, which is 7 pi over 6. And so 2x is equal to 7 pi over 6 plus 2 pi n. And I'm almost done. All I need to do now is divide both sides by 2. So you're going to divide everything by 2. And I'm going to get, for the first one, x equal to 5 pi. If you divide this by 2, it's going to be 12. Plus, and then 2's going to cancel over here, so plus pi n. And then the second answer is going to be divide this by 2, so 7 pi divided by 12. Plus, and then this 2 is going to cancel with the 2 when you divide by it, pi n. where n is an element of the integers. So we use that z looking like thing. So 0, 1, 2, 3, or -1, -2, -3, and so on. Let's check our work just to make sure. So I have, the cosine. So the cosine of 5 second pi divided by 12. And I get back this, So now I know there's a mistake. Right? How do I know there's a mistake? Because that should be negative √3 over 2. I see the mistake. Okay, so what's the mistake? I put in 5 pi over 12 for x, but this is not x. This is 2 times x. So let's fix that, and then that'll fix what I put here. So here's my last entry, and I should have in front of this 2 times that answer, 2 times that solution. And there you go. So that's negative √3 over 2. So negative second square root of 3 in parentheses divided by 2. You'll see those are exactly the same. I should also check the next answer. So cosine of 2 times 7 second pi divided by 12 in parentheses, and I get the same answer. So they work. So my answer for this one is right here. So moving on, we come to trigonometric identities. So there's some basic identities everybody should be familiar with. So the first identity would be sine squared of, and we can use x or theta. Let's use x. Sine squared of x plus cosine squared of x is always equal to 1. One way to remember this is the unit circle. The way you can understand the unit circle in terms of trigonometric functions is that this is always cosine of x, comma sine of x, where x is this angle there. And so obviously if that's cosine of x, sine of x lies on the unit circle, if you square the input plus and you add the square of the output, it should be equal to 1 because that's a definition of this circle. Now there are 2 other identities that follow real simply from this one. So if you know this one, then the other ones are real simple because the other ones are found by basically dividing both sides by sine squared of x. So if you divide sine squared of x by sine squared of x, you get 1. Plus, if you take cosine squared of x divided by sine squared of x, you're going to get cotan squared of x. And if you take 1 divided by sine squared of x, that's going to equal cosecant squared of x. So that's another common trigonometric identity. And then the second one that comes from this, instead of dividing by cosine of squared of x, we're going to divide by, and you can guess it, it's cosine squared x. All right, so the first one was sine squared, now you divide by cosine squared. So if you take sine squared divided by cosine squared, you're going to get tan squared x. And then plus cosine squared divided by cosine squared, it's just going to be 1, equal to 1 divided by cosine squared of x is going to be secant squared of x. So on the side, hopefully you remember there's basically 3, well, really just 2, right? You have the sine of x, cosine of x, and then from cosine of x and sine of x, you can write tan of x, which is sine of x over cosine of x. And then you have these cos over here. The cosecant of x is equal to 1 over sine of x. And the way I remember that is I simply look at the letter. This is a c, and so it's opposite the letter. So that's how I remember it. So cosecant of x is 1 over sine of x, whereas secant of x is 1 over opposite the letter, so cosine of x. And then cotan of x, we can write this as 1 over tan x, or you can write it as cosine of x over sine of x. So these are, if you want some, these are actually definitions over here and identities to the left. There are actually a few more you should be familiar with. So let me remind you. If you have sine of 2x, so you're taking sine of 2 times x, this is equal to 2 sine x cosine x. And then finally cosine of 2x a common identity for this is 2 cosine squared x minus 1. So you've probably seen these before. Now you might not have seen these next two, and these are real important, especially when you start to do integrals, and if you're going on to Calc 2, you'll use these quite often. So if you have cosine squared of x or sine squared of x, you can rewrite this as 1 plus cosine of 2x all divided by 2. And this is basically the same, but instead of plus, you're going to put a minus. So 1 minus cosine of 2x divided by 2. These are typically pretty easy for me to remember. The only one that I typically struggle with, and I find most students struggle with, is sort of like this one right here. But realize that this identity actually follows right from this identity if you solve for cosine of 2x. So if you can remember this one, then you can use that to figure out that one. But these are the standard identities that everybody should be familiar with, and if not, you need to sit down and memorize them every morning. When you get up and you're going through your morning routine, just think about these identities and say them out loud, like sine squared x equals 1 minus cosine of 2x divided by 2, and so on, and it'll be pretty easy to remember. We're going to use these in some problems. So these are trig identities, and we want to pick a side and prove the identity. So the idea is this is going to try to help us memorize the identities that we know and identify them. So you can pick either side you want, the side cubed x side, or you could take sine x minus cosine squared x times sine x. I'm actually going to choose this side to start with because I can see that I can factor out the sine of x just to begin with. So the idea is you start with one side. So I'm going to start with sine of x minus cosine squared x times sine of x. And when I work with this, the idea is to try to turn this side into that side by using the identities I'm familiar with. So what I see here is I can factor out this sine of x. So I really see, in some sense, three things. I see a sine of x here, I see a sine of x here, and I see a cosine squared x there. So I can pull out what I have in yellow. And so this is going to be sine of x something minus something, and the something here is just a 1 because 1 times sine of x is sine of x, and then minus, and the cosine squared x is going to go here. Now when I see this 1 minus cosine squared of x, when I see this 1 minus cosine squared of x, a light comes on in my head and says, oh hey, remember sine squared of x plus cosine squared of x is equal to 1. So I know that sine squared of x is equal to 1 minus cosine of squared of x if I move over the cosine square of x, and that's exactly what I have in green down there. So I can swap out this with sine squared of x, so this is going to be equal to sine of x times sine squared of x, which is equal to sine cubed of x. So therefore, my identity is true. So therefore, I know that sine cubed x is certainly equal to sine of x minus cosine squared of x sine of x. And it does not matter which side you choose. In fact, in part B, I'll start with the left-hand side. So part B, I'm going to start with this left-hand side. So I have tan squared of x. And I want to show it's equal to 1 minus cosine of 2x divided by 1 plus cosine of 2 of x. So when I see this, when I think of tan, I think of sines and cosines. So this is actually sine squared x over cosine squared x. So that's one thing I can do. And then if you look at your trig identities we wrote before, and we're looking for like 1 plus cosine 2x, 1 minus cosine 2x, and you'll see over here, it's pretty obvious what you're going to do. You're going to replace, you're going to use these two identities here, and replace sine squared of x and cosine squared of x with what they're equal to over here. So I come down here, and I simply copy down what they're equal to using the identities. So on top I have 1 minus cosine of 2x divided by 2, all divided by 1 plus cosine of 2x divided by 2. And then that's equal to, if you divide by a fraction, you multiply by the reciprocal, so 1 minus cosine of 2x, all divided by 2, times the reciprocal would be 2 divided by 1 plus cosine of 2x. And so these cancel, and you're left with 1 minus cosine of 2x, all divided by 1 plus cosine of 2x, which is where you want it to go. And so therefore we know that tan squared of x is actually equal to 1 minus cosine of 2x over 1 plus cosine of 2x. Students often struggle with these, and it's not so much the identities you struggle with, it's usually the notation. So it's real important that you can do this and that you don't get confused by things like you try to cancel off these 2's here. You can't do that. This is inside the cosine function. The 2 can never go inside the cosine function. All right, so it's just real important that you feel comfortable working with this in the sense of the notation. And that comes by practice, basically. All right, the last thing I want to talk about are a couple of theorems here. So I'm sure I know we've done this before, the Pythagorean theorem, but I haven't talked about the law of similar triangles. So let's take a look at these two things real quickly. So the Pythagorean theorem, which is basically probably the most important theorem in the calculus that we're doing. And it basically just says, hey, if you have a right triangle, so here's my right triangle, and we label these sides A and B and the hypotenuse C, there's a relationship here, and the relationship is that if you square side A and you add the square of side B, you get the square of the hypotenuse. So hopefully you know that. It's really interesting to go out there and try to figure out why this is true. There's some really interesting proofs, some picture proofs, and if I have time, I'll show you a picture proof of this. And the picture proof just basically shows you a picture in motion and shows you, that explains why this is actually true. The law of similar triangles may not be as familiar to you, but it's a pretty obvious result. So the law of similar triangles. And the idea behind this is if you have two triangles, let's draw it like this. If you have two triangles and they have all the same angles here like this, so you have a big one, oops, let's make that better. So I have this big black triangle and this little green triangle. These are the same sides. I can label a little green one little a, little b, and little c. And I can label the big one, of course, this side is capital A, capital B, and capital C. And then what I know about the ratios of the sides of these triangles should all be the same. So if you want, we could write like little a over capital A will equal little b over capital B, which will equal little c over capital C. And so this is the law of similar triangles. Basically, if the two triangles have all the same angles, have congruent angles, then this equation, these ratios will all be, this equation will hold and the ratios will be the same.